In this video, we're going to talk about secants and tangents. So what are secants and tangents? Well, luckily we have a whole bunch of definitions here to help you understand what they are. So a secant is a line that intersects a circle at exactly 2 points, and every secant contains a chord. So if I have a circle, this is a secant, right? It intersects at 2 points. There's a chord that it contains. Tangent. It's a line that intersects the circle at exactly 1 point, called the point of contact. So if I take the same circle and do this line intersects this circle at 1 point only. That is the point of contact. We say this line is tangent to the circle. And it has a couple properties too. So properties of tangent lines. If a tangent line is perpendicular, a tangent line is perpendicular to the radius drawn to the point of contact. So if this is the center of the circle, and I draw the radius from the center to the point of contact, these lines are perpendicular. There's a right angle here, okay? And that's no matter where the tangent line is. 2, if a line is perpendicular to a radius at its outer endpoint, then it is tangent to the circle. And this is just kind of going the other direction. So if I say, hey, here's a radius, here's a line, look, these are perpendicular. That means this must be tangent to the circle at the point where the radius hits the circle, okay? Tangent segment is the part of a tangent line between the point of contact and a point outside the circle. So if I drew a circle and I have a tangent line like this, and let's say I have another point out here, this would be a tangent segment right here. Tangent segment. Secant segment, the part of a secant line that joins a point outside the circle to the farthest intersection point of the secant and the circle. So if I have a secant line like this, that intersects at these points, then my secant segment would be this whole thing here. This is my point outside the circle, and it connects it to the farthest point of intersection of the secant and the circle. The external part of a secant segment is just this bit here, the part that connects the point to the closest intersection point. So this is just the external part of the secant segment. Okay. Tangent circles are circles that intersect at exactly 1 point. So if I take a circle here, and I have another circle here, those are tangent circles, right? They're intersect at only 1 point. A common tangent is a line tangent to 2 circles. So if I draw, one other terminology with tangent circles, sorry. Here for tangent circles, would be considered externally tangent, because the one circle is not inside the other one. But you could also have internally tangent circles, where I could have something like this, where these circles are internally tangent. They still only touch at 1 point, but one is actually entirely contained within the other circle. Okay. Common tangent, line tangent to 2 circles. So if I do this, and this line would be considered a common tangent to both of these circles. Okay. And then the two-tangent theorem. If 2 tangent segments are drawn to a circle from an external point, then they are congruent. So if I have a circle here, and let's say I have a point here, and I'm going to take a tangent segment there, and a tangent segment here, tangent at this point, and they both join the same point, this has to be the same as this. They have to be congruent. Okay. That's the two-tangent theorem. Okay, so let's move on to some examples here. So I have this setup of 2 circles with some tangent lines. I'm told that segment xy, this is a y, is a common tangent to both circle P and circle Q at point X and point Y. And XS, line segment XS, is tangent to circle P at point S, and segment YT is tangent to circle Q at T. Okay, and we want to prove that XS equals YT, so that these 2 line segments here are congruent. So we want to prove stuff, so we're going to do a 2-column proof. So I'm going to set this up just by starting to list things that I know, right, that are given to me. I should switch colors. Let's do blueberry. Okay, 1. So first I know that line segment XS is tangent to circle P. And I also know that line segment YT is tangent to circle Q. How do I know that? Because it was given to me. What else is given to me? Well, I also know that XY is tangent to both circle P and circle Q at the points at X and Y. And that was also given. Okay, so what conclusions can I draw from this? What can I do here? So what if we look at segments XS and XY? Okay, so this segment and this segment here. I know here that this XS is tangent to the circle. XY is also tangent to the circle P. Okay, so these two segments are both tangent to the circle, and they join at this point outside the circle. So they have to be congruent based on the two tangent theorem, right? So I can say this is tangent to this. And then I'm getting ahead of myself, because we're trying to prove these two things are equal. And if this is equal to this, right here and here, then we can make the same argument and say that this is also equal to this. And then by the transitive property, this is equal to this. So we've proved it. So I'm just going to write it out now in proof form. So line segment XS is congruent to line segment XY because of the two tangent theorem. I like that. TTT. Nice. 4. Yeah, two tangent theorem. Is XY is congruent to YT because of the two tangent theorem. And number 5, we can then say that XS is congruent to segment YT, which is what we wanted to prove, because of the transitive property. Transitive property. Okay, and we've proven it. We're done. So the two tangent theorem, very, very, very helpful in this situation. All right, let's do another one. So now I have this circle O. I have, this is obviously not drawn to scale because my 6mm line is much longer than my 8mm line, but I am not known for drawing things to scale, so sorry. Things that I know here. I know that TP is tangent to this circle. That's just something given. I should write it. TP tangent, oops, that's perpendicular. Tangent to circle O. And this radius is 8mm long. This segment is 6mm long. I want to find line segment OP. Well, here this is actually pretty straightforward because I was told that if a line is tangent to a circle at a point that is an endpoint of a radius, then the radius and the tangent segment are perpendicular. So this is a right angle. And once I know this is a right angle, I can use the Pythagorean theorem, right? I can just say that OP squared is equal to 6mm squared plus 8mm squared. So therefore, line segment OP is going to be equal to 10mm. Great. About 10mm. Yeah. Actually, no, exactly 10mm. Cool. So that's number 2, where this kind of right angle theorem is helpful. Okay. Example 3. So here we want to find x. And what information do I have here? I have that this line is a common tangent to both circle Q and circle P at the points A and B. Okay, so we'll say AB is common tangent to Q and P at A and B. Okay. So how can I find x in this case? There's actually a whole method here. The easy way to summarize this is make rectangles and triangles. And once you do that, it becomes a lot easier to solve. So we're going to draw a rectangle that, connects my center to this line segment and is parallel to my tangent line. And then I'm going to draw a triangle that closes off the rest of this here. Okay. And once we do this, the problem actually becomes much, much easier to solve because I know the length from here to here is 18. I know that this is a right angle, right? Because these two lines are parallel. I know from P to this point in between is going to be 8, right? Because that's the length of the radius of the circle. And then I know that this is a rectangle, right? So if this is a rectangle, if this is 8, this must also be 8, which means, you know, I am famous for not drawing things to scale. This line segment here is 10. Okay. So we know this is 10, this is 18, this is 8. And now I can find the length of the leg of this triangle, which is going to be this same as x, right? I can just do that with Pythagorean theorem. I can say that line segment QR squared, I guess I should label r, huh? I'm going to call r at this point is r. So QR squared plus RP squared, which is the leg, is going to be equal to QP squared. So that's going to be 10 squared plus RP squared is equal to 26 squared. All right, 18 plus 8 is 26. So then RP, if I solve this out, is going to give me 24, which means that line segment AB, which is equal to x, which is what I was trying to solve for, is also going to be equal to 24. Okay, so anytime you have a common tangent, try to draw rectangles and triangles. And then once you do that, the problem, you're just going to fill in everything you can, and you're going to end up doing like a Pythagorean theorem in the end to solve it. Okay. So one other special kind of case where you have to do something a little weird to solve it is in this case where we're using something called the Walkaround method. Okay. So I have a circle. It has 4 tangent segments. Each side of this quadrilateral is tangent to the circle. And I want to find the length of side CD. I have to give you a little bit more information to do that. So let me fill in some info here. I'm going to say that this full side, BA, is 10. Okay. So that side is length 10. This side is length 15. And this side is length 18. Okay. So now here's how you solve this. We're going to call the length between B and E x. Okay. Now, because of my two tangent theorem, I know that the length from B to E has to be the same as the length from B to this point here. So this is also going to be x. Okay, since it's tangent at 2 points and they connect to the same point outside the circle. So if this is x, that means E to A must be 10 minus x. Okay. And that means here to C must be 15 minus x. Well, you can see what I'm doing is I'm kind of walking around and I'm just filling in everything I know. So then over here, from A to this point of intersection, this is also going to be 10 minus x. Because again, if I have AE and I don't know, I'll call this F. AF, right, are 2 tangent segments. And they have an endpoint at the same point external to the circle, and they're both tangent to the same circle, so their lengths have to be the same. Okay, 2 tangent theorem. So if this is 10 minus x, then this length from F to D is 18 minus 10 minus x. Right, because these two things together have to add to 18. And then I'm going to come over here, and I know if this is 15 minus x, then this segment must also be 15 minus x from here to here. We'll call it EF, we'll call this G and H. And then this segment here has to also be 18 minus 10 minus x, because these have to be the same. Okay. So then I want to find CD, right? So CD is going to be equal to 15 minus x plus 18 minus 10 plus x, where I'm just distributing the negative sign into the parentheses. So my x's actually cancel out. And when my x's cancel out, I do 15 plus 18 is 33, minus 10 is 23. And that's it. So when you have a problem like this, it looks like you don't have enough information to solve it. But just by using two-tangent theorem in every single corner of this polygon, you're then going to be able to solve it in the end because your x's will hopefully drop out. Okay, so those are some cool properties of tangents and secants and how you can use them to solve problems. Thanks for watching.